Hey guys, my name is Trevor Sullivan and welcome back to my video channel. Thank you so much for joining me for another video in our Rust programming tutorial series. Now, in our last video, we introduced the concept of async operations in Rust, and we saw how that allows us to build applications that have the feeling of improved performance, but only because we're allowing tasks to kind of interoperate with each other and pause execution temporarily while other tasks can run on a single core processor. Now, async is not the same as multi-threading, where we can actually do work in parallel with each other. Instead, async is what we call concurrent programming, where we can have a lot of tasks in an actively running state, but only one of those particular tasks is actually going to be able to get processor time at a time. Now, there's another crate out there called Tokio, and this is probably the most popular asynchronous runtime for Rust. As we discussed in our last video, we need a runtime executor in order to actually execute async tasks. Otherwise, there's nothing to kind of push them forward. There's nothing to call that pull method on a future. So in this video, what we're going to be doing is actually taking a look at something a little bit different than Smol, which we used previously. We're going to be looking at Tokio instead, because Tokio is a much more robust library. It provides asynchronous APIs for things like file system operation, network socket operations, and things of that nature. And again, this is a really popular library, so there's a lot of momentum, there's a lot of support behind it. And if you're building a production grade application, Tokio is most likely the crate that you're going to want to look to in order to do asynchronous, but you can also do multi-threading with it very easily as well. So we're going to take a look at how to use Tokio, but we're going to add a second really important concept to this video, which is how you can actually implement your own custom future as well. Back in the video where we introduced Smol and futures, we discussed how we can use the async keyword in front of a function to make that function asynchronous, but you can actually implement your own custom data structures that track their own separate internal state and implement the future trait from the standard library, and then we can use a runtime executor, async executor like Tokio or Smol to actually drive our own custom types to completion because they implement future as well. So we're going to be covering a lot in this video, but for starters, I just wanted to introduce Tokio here and kind of go over some of the fundamentals of the Tokio APIs so you have a better idea of where it's going to be applicable. And we're also going to take a look at how to do single-threaded versus multi-threaded operations in Tokio here as well. So for starters, let's take a look at the documentation here for Tokio. So if you go over to the Tokio website at tokio.rs, and that's Tokio for anybody who's listening and not watching this video, then this website is just kind of the landing page for Tokio. They do have some decent documentation over here. So if you're brand new to Tokio and you're looking for more of a beginner's guide to its capabilities, this is a really great place to look. But if you are a little bit more experienced with Rust, if you've been kind of following along so far, you probably have kind of gotten the idea that the authoritative documentation over on docs.rs, that's kind of the main documentation site for various Rust libraries, this is really the best place to go to find the authoritative documentation for how various APIs are going to work. Now, one thing I do want to point out is that Tokio as a crate, as a dependency, is actually broken down into lots of child dependencies. So there's a lot of different features that you can enable or disable in the Tokio crate. Now, if we do a regular installation of Tokio, there's going to be some essential features that you might expect to be available that aren't going to be installed again by default. So we will need to make sure that we tack on some features. As you can see in the documentation here, they actually recommend that you go with the full feature set if you are new to Tokio so that you don't run into any roadblocks. But personally, I actually kind of like running into those roadblocks because you do get some pretty quick feedback from the Rust Analyzer extension for VS Code that kind of indicates to you that a particular feature is missing. So you can just go back to your command line, do a cargo add, specify which missing feature you want to install, and just pick up from where you left off. And that helps to keep your binary size a little bit smaller, your compilation times are going to be a little bit faster instead of just going with the full feature set. That's kind of a nice crutch to have as a fallback option, but I would really encourage you to just kind of practice with installing a base feature set and then just adding the specific features that you need. Now, if we take a look at something down here called attribute macros, this is really the main way that I think most people are going to use Tokio, by using this special macro down here called main. And the main macro is something that you can do to your main function in your Rust application in order to designate that you want Tokio to basically wrap up that main function as an async function that's going to be your entry point into your application. So when we apply the main attribute from the Tokio crate to our Rust main function, that will actually allow us to define our main function as an async function, whereas normally if you're not using an async executor, then you won't be able to have an async entry point into your application. So we're typically going to want this feature down here. And what I want you to take note of is that in this little kind of blue background text right here, after the name of the attribute macro, it actually tells us right here in the documentation which specific crate features we need to enable in order to have access to this specific macro. Now, RT, which is a child feature of the Tokio crate, and macros, which is another feature of the Tokio crate, those are not actually installed as part of the default feature set for the Tokio crate. So if you just do cargo add Tokio to your Rust project, those RT and macro features aren't enabled. And so by default, you're not going to have access to this main attribute macro here, so you won't be able to create an async main function. So all we need to do is make sure that we install either RT or macros features for Tokio, and that will enable this attribute macro to be available. And this actually applies to other child modules of the Tokio crate as well. So one of the nice things about Tokio is that we have the file system operations here that are asynchronous. All of those are kind of wrapped up into their own separate module. And you'll see again in this blue background text right here that there's actually a crate feature called FS that allows us to include the file system async operations in our Rust project. Now, if you don't plan on doing any, IO, or if you're not planning specifically to use async IO, then you don't have to include that feature at all. Same thing for process management here. If you're not planning to asynchronously kick off any external Rust commands, then you don't need to include this particular feature in your project, and that helps to keep your resulting binary a little bit smaller and your compilation times shorter. Also, there's a signal crate feature here that allows you to handle operating system process signals like sighup, sigkill, terminal window resizes, things of that nature. So this is actually a really cool thing that allows you to respond to operating system level signals from both Windows as well as Unix. So it is compatible with both of those. There's also things for working with time operations down here, but anytime that you see one of these crate features, that is just going to indicate to you what you need to enable in order to get access to those particular features. So once we kind of drive into the main feature of Tokio, which is the async executor, what they call the Tokio runtime here, you're going to notice that we need the RT feature in order to get access to the types that are exported by this particular module here. So again, depending on which macros or modules you want to import into your application, you might need to enable certain features, and we'll take a look at how to accomplish that. Now, in addition to using the main attribute macro, there's actually a second syntax that we can use to build an async executor runtime using Tokio. So using the attribute here is pretty straightforward. All we do is add the Tokio main attribute to our asynchronous main function. But inside of this runtime module here, we also have this thing called a builder. And this allows us to basically build out a Tokio runtime instead of using the attribute macro called main on our entry point. So in that case, we would have a synchronous main function, but then inside of that synchronous main function, we can create an async runtime and then call certain functions on that runtime in order to perform async operations in a blocking fashion. If you remember the video that I did previously in this Rust playlist, that covers kind of an introduction to async operations in Rust. And using the smol executor, we actually used a function in smol in order to call block on. So let's search for block on here. And so Tokio actually has a similar function here on the runtime that allows us to basically just pass in a future and block the main thread until that future has completed. And so that way our main thread isn't going to exit and cause the future to be aborted before it even has a chance to run. So we're going to go ahead and take a look at how to include Tokio in a project and just kind of get started completely from scratch. We're not doing any copy paste pasta type of things in this video because I really want you to be able to implement this on your own in your own project completely from scratch. So what we're going to do is jump over into VS Code here, and we're going to create a brand new project. We'll include Tokio. We'll take a look at the attribute macro called main that allows us to kind of denote that our main async function is our entry point to our asynchronous program. And we're also going to take a look at how to enable multi-threading, and we'll take a look at how to use that builder pattern for starters in Tokio. And if we don't have time in this video to get to implementing a custom feature, then we'll go ahead and do that a little bit later on, maybe in a different video, but I'm kind of hoping to package all this stuff up together in the same video. Now, before we get into the actual content of our hands-on demo, I wanted to invite you to subscribe to my channel. I'm an independent content creator, so any kind of support that you lend to this channel helps me to bring you content on Rust and other types of open source tools. So head out to my channel, youtube.com/TrevorSullivan. Check out my Rust programming tutorial playlist down here. Also, if you learned something from the video, please leave a thumbs up or like on the video to let me know that you learned something. Also, leave a comment down below. Let me know what kind of things you're interested in seeing on my channel, and let me know your thoughts on this video. And also check out the pinned comment. Those affiliate links help me to fund the development of future content for this channel. So please use those affiliate links if you're going to make a purchase, and that'll help me out a lot. So in any case, let's go ahead and spin up a project here. I'm on my Rust server here, so I'm on a remote Linux VM, as I often am in most of my videos. I think there was one video where I used Windows locally just to kind of simplify things, but in general, I'm doing my development against a remote Linux VM. So what I'm going to do is just make a project folder here. So we'll say async with Tokio. I just want to make sure there's no naming conflicts with crates or anything like that. So we'll cd into that directory. We'll do a cargo init just to create a Rust binary, and we'll do Control-K, Control-O to open that up inside of our editor here. So async with Tokio, and that'll just cause the VS Code window to refresh. All right, so you should also have the Rust Analyzer extension installed because that is how we get things like auto-completion and all that fun stuff. And I actually cover kind of the whole dev environment setup process for Rust on a Ubuntu Linux headless server in my very first video in that Rust playlist. So make sure you go check that out along with all the other videos in the series. All right, so inside of our project here, the first thing we want to do is bring in Tokio as a dependency. Of course, we've got our default main.rs file here with hello world, but we're going to just eliminate this, and we're actually going to turn this into an async main function. Normally, if you just plug in the async keyword there, you're going to see that Rust doesn't allow you to have the entry point of a Rust application be async because, again, there's no executor. There's nothing to pull the future and actually drive it to completion, and that's why we need to use Tokio. So down in our terminal, we're going to just do a basic cargo add Tokio, and this will install the default feature set. Now, as you can see, there are a lot of features here that just barely fit on the screen here that are disabled by default. Over in the Tokio documentation, we saw that the async file system operations are not included by default. We've got things like macros that enables the attribute macro called main that we can use to annotate our main function as our entry point. We've also got RT and RT multi-thread. So if we want to do a custom Tokio runtime using the builder type, or if we want to do multi-threading in Rust, then we also need to enable the RT multi-thread feature in order to use that functionality. So we need to go ahead and, for starters, try to do this Tokio main attribute on our main function and we're going to get this error that says, hey, it couldn't find main in Tokyo. And this is because we have not enabled the necessary feature from the documentation in order to use that macro. So back at the root crate here, if we scroll all the way down to attribute macros, it tells us right here, either enable RT or enable macros, and that will allow us to use this macro, this main macro in our project. So once again, we'll just do cargo add Tokio -- features equal macros. And now we've got macros and Tokio macros here, and we should be able to use that annotation. Now, it may take a moment for the Rust analyzer to kind of get all the metadata, all the IntelliSense analyzed here. But once we enable that, now this is a valid reference here. We can even do use Tokio, and we should see main show up in this list here. Now, we're getting another error here because it's telling us that in order to use this main macro, we have to import the runtime or the multi-threaded runtime for Tokio. So once again, we're going to have to go down here, look at this feature list and say, well, I need the runtime, the Tokio async runtime, so I need to enable the RT feature here. So once again, we're just going to say cargo add, and we'll just add the standard synchronous runtime rather than the single-threaded runtime versus the multi-threaded runtime. So now in our attribute here, it says the default runtime flavor is multi-threaded, but we have not enabled the multi-threaded feature. So now if we take a look at the documentation for this main attribute macro here in Tokio, we're going to see the syntax that we can use to specify the threading model. So again, the default, if it's not specified, is going to be multi-threading, but we can actually pass in this flavor parameter to the attribute macro and specify that we want it to use current thread. In fact, our editor even helps us out with that. So when we type flavor here, unfortunately, autocompletion doesn't work for that. But if I specify an invalid value like ASDF, you're going to see this error come from Rust Analyzer saying that there is no flavor called ASDF. The only supported flavors are current thread and multi-thread. So even though the auto-completion doesn't work in Rust Analyzer, it does still, the error messages do still tell you what works and what doesn't. So if I do accidentally an S on the end and say current threads, well, that doesn't match the desired value. So it's going to throw an error there. All right, so that's how we can switch it from the default multi-threaded to the single-threaded model. All right, so now that is going to work just fine. We've installed the necessary features. We switched from multi-threading to single threading, and now we should be able to compile our application and it should run just fine. But right now the application isn't actually doing anything. So how do we actually do something inside of this function? Well, for starters, because we now have an async main entry point here, we can call other async functions. So if I have an async function that says test something and a print line, hello from Tokio, put a semicolon to terminate that line, and then just call the test something function from our main function. Remember that async functions here return futures. And so in order for this to actually execute, we need to await that future. And that will tell the Tokio executor that we want to drive that future to completion before we proceed with the main function execution. So now we get hello from Tokio in our output here. Now, at the moment, we're not really doing anything that would necessitate having multiple threads, but I just wanted to show you how we can kind of prove the number of threads that are being spun up. So what I'm going to do is just put a little sleep in here. So we'll say standard thread sleep, and we'll say standard time duration because the sleep function takes a duration as input. And then we'll do from millis and say, I'm going to wait for, how about 5,000 milliseconds, which should be 5 seconds, right? So it's going to sleep for 5,000 milliseconds and then print out our statement. But before we actually run this, what I want to do is bring up a separate terminal right here. And I could do this in VS Code, but I would probably block it. So I'm just going to spin it up in this separate window. And we want to use this utility called btop, which is basically just a process monitoring tool. And it does require a minimum size for our terminal here. But I'm going to hit the minus sign a few times in btop, and that should decrease our refresh time up here. So by default, our refresh time is 2000 milliseconds. And for some reason, it's not responding to my attempts to decrease that. So we'll just leave it at 2000 milliseconds for now. But now I'm going to do a cargo run, and we're actually going to hit F to filter the process list really quick here. So let's do F to filter. It actually doesn't look like it's taking any input from me for some odd reason here. Now it seems to be working. So I'll bump my refresh speed down to 500 milliseconds, and then we'll hit F to filter, and we'll say cargo. Right now we're not running anything under cargo, so nothing is going to show up. But if we do cargo run and then immediately switch back, let's try target here. Sometimes it shows under cargo, sometimes it shows under target. So let's try with target here and see if it shows up. No, let's do cargo again. All right, so I'm going to disable with 2 and 3. Let's do a search there and then say 2, 3. That'll kind of expand the process window so we're not looking at memory or network IO information. And now we can see this field here called threads that was hidden just due to the size of my window. And so now if we do cargo run, see, it doesn't show up under cargo this time for some reason. So let's see why that's happening here. Let me actually just change it back to target here. Okay, so as you can see, I think just for a split second there, you can see that the thread count is 1, right? And that's because we changed multi-threading to single threading. But let's say that we wanted to change this back to multi-threading so we can actually run multiple futures in parallel and let the Tokio Executor runtime figure out which futures to execute on which threads, right? On which CPUs. So what we're going to do is change the flavor here back to the multi-thread. So we could either eliminate flavor entirely, or we could set it to multi_thread right here. And now we're going to get this error once again saying that we don't have the multi-threaded runtime installed. So we'll need to do a cargo add and specify the feature called RT-multi-thread. So we'll say features equals RT multi-thread, and that should include that feature now. So if we come back to our code editor, everything looks just fine here. Now, if we do cargo run, we should be able to see that there are multiple threads spun up. So let's come back here, say cargo run again. So now we can see that 4 threads are spun up. And the number of threads is actually determined based on the number of CPU cores that you have. So as you can see on this system right here, I have 3 CPU cores, 0, 1, and 2. Plus, we also have the main thread. So there's 3 worker threads, 1 for each CPU core, and the main thread, which totals up to 4 threads there. Now you can optionally specify the number of threads that you want as well. I think there's actually another parameter on here called worker threads. So we could go to the main attribute macro and say, all right, I want worker threads to be 10, and that'll spin up more threads. So what we'll do is come back over here and say worker, what was it called? Worker threads equals, let's say 10, do a cargo run and switch back here. And so now we have 11. So 10 worker threads plus the main thread, that results in 11 threads. So Tokio not only handles executing the executor role as kind of pushing futures forward, but it also allows you to spin up multiple threads. And then the Tokio runtime, when you spawn off these async futures, it'll actually assign each of those futures to a thread. So now what I want to do is actually take a look at how to implement a custom future by implementing the future trait, which is built into the standard Rust library. And this will allow us to create our own custom types in our application that are futures. And then we'll use the async multi-threaded Tokio runtime in order to actually execute that. All right, so I'm going to comment out this function right here, and we'll comment out that call to it. And for this particular example, what I'm going to do is use kind of racing as an example. So I'm going to call this an F1 racer. And so if you think about an F1 racer, you know, they've got those fast cars and they go around some kind of track and they do maybe a bunch of laps, right? Maybe 5 or 10 laps. So what I'm going to do is basically represent one of these racers as a construct, and then we're going to implement future on that. And then we'll create multiple instances of these racers, and we'll try to discover what the best lap time is for each of these racers. That'll be the results that we want to ultimately get back from the future. But every single time that they do a lap, we want to basically allow the future runtime to execute other work. So if, maybe one guy does a lap, somebody else does a lap, then somebody else does a lap. So we want to be kind of fair with our scheduling and carve up our entire race as different laps. And then each of those laps is a separate unit of work that the executor can delegate to a particular thread. So it's all a little bit confusing. I would not blame you if you felt a little bit confused by this stuff, but we're going to go ahead and implement this, and hopefully it makes a little bit more sense as to how it works. And we can also dynamically determine which thread we're executing on, so that way we can see in the actual output the different racers getting assigned to different threads, and even the different laps that each racer has completed getting assigned to different threads. So what we're going to do here is start by defining just a simple data structure. And this data structure is going to represent whatever object it is that we want to create in our application. So I'm going to call this an F1 racer. So an F1 racer is going to have a name, and we'll just set that to a string type. And we'll also say completed laps. So this will keep track of how many laps the racer has completed. We'll also keep track of the number of laps that we want the racer to complete. So that'll be an unsigned 8-bit integer as well. So we have a name, we have completed laps, and we have a total number of laps that we want to complete. So for now, that should work all right. And we also want to have a best time. So we'll say best lap time, and we'll just do that as a number of seconds for now. And so we'll make that a U8, and we'll just assume that they can do it in under 255 seconds. But of course, you could use whatever unit of measure, whatever data type, like maybe a U16 or something like that as well. All right, so now what we want to do is to implement a type that allows us to easily construct new racers. So I'll just do impl F1 racer here. And we're going to create a new function so that we can instantiate a new racer. And so inside of this here, we'll just say return F1 racer, and we'll go ahead and construct one with some default values. And of course, we want to specify that it's going to return an F1 racer as well. And then so right in here, we're just going to give it a name. And so I'm going to use a name of like Max Verstappen. He's a F1 racer. And we'll also do number of laps that we want to complete is, let's say, 5 laps. And then we'll say completed laps. That'll always start at 0 because when you start a new race, you haven't actually done any laps. And the best lap time, I'm actually going to set this to the maximum value of an unsigned 8-bit integer, which should be 255, because the first lap that we do should be some number under 255, like maybe, I don't know, 85 seconds or 80 seconds or something like that. So we want to start with the assumption that the worst lap time is going to be the default. And then once you complete the first lap, which let's say it's 85 seconds, then we'll assign that new value to the best lap time. Now, we can always override these values too, just by making this a mutable value once we construct it, but this will just help us to instantiate new objects and then just allow us to override any values that we want to. Now, the other thing that I'm going to do, and this might seem a little bit weird from a data structure standpoint, but I'm going to specify the lap times for each of these individual racers as a vec. So we'll do a vec of U8 here. And this is going to basically contain their lap times so that when we actually pull the future, we actually know what the current lap time is each time. And so we can just kind of customize that every time that we construct one of these new racers. So what I'm going to do for lap times here, I want to make sure that I have a vec of U8s, and I'll just do something like 87, maybe 64, maybe 126, maybe 95, and how about 76? So we want to make sure that we have a number of lap times that corresponds to the total number of laps that we are going to complete. And the way that I'm going to implement this as well, I'm actually going to be pulling a value off of the end of this vec. So 76 is going to be lap number 1, 95 will be next, 126, 64, and then finally the fifth lap will be 87. And then we can always override those values anytime that we create a new racer. So let's go ahead and implement the future type as well. So this is where things get a little bit more interesting. So we want to implement standard future for the F1 racer type. Now this future type here, this trait that we want to implement for our custom data structure here, defines two key things that we need to provide. So first of all, we have the type of output that the future is going to provide. So when the future completes and it's done computing, then we want to return some value. And a few minutes ago, I think I mentioned that we want to return the best lap time for a particular racer. We don't care about how many laps they've completed or the total number of laps that they've done or anything like that. All we want to get back from the future is what is the best lap time for this particular racer. So the output type is just going to be a U8 that represents the one best lap that that particular racer had. Now, the meaty part of the future trait here is something called the poll function. The poll function is what the executor runtime, so in this case, Tokio, or in my other video, we used small. The poll function here is going to be repeatedly called by the executor, and that's what's going to ultimately drive the future to completion. So the poll type here, or the poll function, not type, is going to return standard task poll. And once it's completed, it's going to resolve to the output type that we specified right up here. So this poll function at the final completion needs to be able to return a ready value that wraps the final value that we want to return to the caller. So essentially what we're going to do here is return whatever self.bestLapTime is, because that's the value that we're trying to get at, right? But we can't just return the U8 value by itself. We actually need to return standard task. That's a child module called task. And then we have this poll enum, and it has two variants. We've got pending and ready is what wraps the final value. So we'll say self.bestLapTime is the value that this variant for the poll enum wraps as the final result. So now that satisfies the return type of this function. But at the moment, as soon as a new racer is created, the very first time that this poll method is called on a racer is just going to immediately return the best lap time. And what is the best lap time? Well, anytime that we initialize one of these racers, we're defaulting it to 255. So we would just get 255 back. We're not actually going to see any of the individual lap times that we have right here. So we actually have to implement some logic for the racer to race these laps, right? So first of all, we need to increment completed laps until it reaches the final number of laps here. And we also need to iterate over each of these lap times here. And it's going to be in reverse again, but we need to iterate over each of these and see if the number is better than the previous value. And if it is, then we want to assign it to the best lap time. So the first time that we run the poll function, we should have 76 rewrite the value for best lap time. Then 95 is greater than 76, so that's not as good, so we just discard it. Then we go to 126. Well, that's not as good as 76, so we'll discard it. Then we go to 64. Well, 64 is a better lap time than 76, so best lap time will get updated to 64. And then on the final lap of 87, that's not as good as 64, so we just discard it. So we should be getting a final result of 64 as an unsigned 8-bit integer from the future here. And again, we can kind of test things by just customizing these values for the lap times, running through the future, and making sure that it returns truly the best lap time. So I know that probably all sounds a little bit confusing, but hopefully as we implement the functionality inside of this poll function, it starts to make more sense to you. So in the poll function here, the first thing that we want to do is to kind of grab one of the lap times. And that's only if we still have lap times available inside of this vec, right? So we want to inspect the vec to see if there are any lap times, and then we can go ahead and either update the value of best lap time or not, depending on what the actual value is. So let's say let lap time equal the self dot laps, and then we're going to pull a value off of the end. So we're going to go ahead and grab a value off of this vec. So the vec is called lap times. So down here we'll say self.lap times, and then we'll pop a value off of the end, and that will decrease the size of the vec by 1. So every time that we pop one off the end, that value will get returned to us. All right, so the current lap time is whatever self.laptimes.pop is. Also, you're going to see that self is not mutable here. So we need to actually get a mutable reference to it. So what we'll do is say self.getMute, and that should allow us to pop a value off of the end. And then that'll assign it to the result right here. And then we can basically do an if statement to see if we want to update it or not for the best lap time field. Now, before we attempt to pop a value off the end here, I want to check to make sure that the number of completed laps is less than the number of laps that we want to complete. So basically what we'll say is if self.completed laps is less than the self.laps, only then do we actually want to grab a new time. Otherwise, we'll have finished the race. And what else I'm going to do here is I'm actually going to move this logic to get the current lap time and kind of update everything into the F1 racer type here. So what I'm going to do is create a function here called doALap. And then inside of this function, we're going to take a mutable reference to self, and that'll allow us to call doLap on each instance of the F1 racer. This one up here doesn't take self as input because this is a function that's going to be associated with the type itself, not an instance of the type. So that's why we take mutable self as input down here, because this is actually affecting a specific instance of F1 racer. So what we're going to do is say let lap time equals self, and then we don't need get mute anymore because we already have a mutable reference. And then we're going to pop a value off there, and that'll give us an option wrapping U8. So now what we'll say if the lap time, so if the current lap time is less than self.best lap time, then we want to update the best lap time with the new value. And of course, this is an option here. So what we're going to say is if lap time dot is some, because we want to make sure it has some value and it's not none. And then we'll say if self dot best lap time dot unwrap, I think. Let's do best lap time, or actually it's lap time dot unwrap is less than self dot best last time. So basically what we're saying is we want to make sure that lap time is some value, not none. And then down here, we want to unwrap the actual value and compare it to best lap time, which is also an unsigned 8-bit integer. So we have to call unwrap to get it out of the option. And then up here, what we'll do is say self dot best lap time equals lap time dot unwrap. So now every time that we run do lap, if the current lap time is better than the current best lap time, then it'll go ahead and update it. The other thing that we want to do in do lap is make sure that we increment the number of completed laps. So what we'll do is say self.completed laps plus equals 1, and that will increment our number of completed laps until we eventually get to 5 laps. And then let's see, what else do we need to do here? So we're incrementing the number of completed laps. We're updating the best lap time. And so what we want to do down here is call self.doLap, and that will allow us to actually invoke a lap. And then if we do a lap and we have more laps to complete, then we want to return standard task poll, and we're going to return pending instead. So what this is going to allow us to do is complete a new lap, and then we're going to return control back to the executor. So we're basically going to be kind of polite to the executor and say, hey, I did a little bit of work. I did one little unit of work. So I'm going to give control back to you. And if you want to do anything else on that thread that I was using previously, feel free to, but I still need to be woken up because I have more laps to do, right? It's not until we actually call standard task poll ready that our future is completed and the output value is returned back to the caller. Now, in order to fix this little error right here, it says we can't mutate self. So we're going to say .get mute here to get a mutable reference to self, and then we'll call do lap on that particular instance. Now, at the moment, this particular future is going to execute poll once, and it's going to completely hang. It's never going to rerun the poll function repeatedly. And the reason for that is because when you're implementing a custom future, you have to make sure that you wake the future up. So you have to indicate to the executor, in this case Tokio, that this is ready, this future is ready to do more work, which we've already kind of done here. But if we go into this context right here that the executor passes into the future when it calls the poll function, there's actually a wake function on here. It's called waker, and that gets access to a waker, and then we can call this function down here called wake by ref, and that will basically tell the executor that it's okay to call poll again because this needs to be woken up. So we've already done all the work that we need to in this do lap function right here, but we need the executor to try to wake us up again. All right, so let's go ahead and maybe test out this code and see if it's going to work all right here. So we are updating the best lap time, popping off a time on the end. We are setting the number of completed laps here. And so we can go ahead and try to instantiate our racer and execute it. So we'll say let racer01 equal F1 racer new. And that'll just give us a default configuration of a racer based on the parameters that we specified right down here. And then we want to make sure that this is driven to completion. So because we are operating inside of an async main function, all we have to do is say racer01 dot await, and that will await the function here. Also, I want to print some debug statements here. So we'll say print line doing a new lap, and we'll also put the person's name in here as well. So we'll say person is doing a new lap and then pass in self.name right here so that we can see that happening. And we might want to do some more debugging statements and say print line racer has completed all laps. And once again, we'll pass in self.name. Now, remember that after we await this result here, the final result based on this output type down here is going to be returned back to the caller. So we can actually capture that after awaiting the racer01. So what we'll do is say let best lap time equal the final result of await here, and that's going to be the unsigned 8-bit integer that only contains the final result from that racer. So we'll say print line and best lap time was X, and we'll just pass in best lap time. All right, let's give this a run and see how things are working so far. So as you can see, it says Max Verstappen is doing a new lap, 1, 2, 3, 4, 5, and then finally Max Verstappen has completed all laps, right? Now, remember we talked about multi-threading and how each unit of work, each time that we call the poll function on a future and do some more work, that work can be scheduled on a particular thread in a thread pool that's been spun up by the runtime. Earlier in this video, we discussed how to set up multi-threading for the Tokio runtime, which again is the default. And by default, it has a single worker thread for each CPU core plus the main thread. But in this case, we actually overrode that and specified that we want 10 threads. So how do we actually see if multi-threading is working or if it's not working? Well, all we have to do is go into our poll function right here and say print line, and then we'll say thread assigned is ID X. And then we can go to the threading library. And I've actually got some other videos in this video series that talk about threading and scoped threading and things of that nature. So you can actually do threading without using an async executor at all. You can just use the standard library. But in order to get the thread ID, we actually want to reach into the standard library and say standard thread. And then we want the current thread. So we're going to call this current function right down here. And then for the current thread object, we want the ID function to return the ID of the current thread. And so now every time that we call this poll function right here, we're going to get the ID of that thread returned to us. And then we'll just do colon question mark here to turn that ID into debug output so that println knows how to format that for its output. So now we'll do cargo run. And as you can see, the thread that's assigned for every iteration here is thread ID of 1. Now, I'm not sure why it's choosing the same thread every single time here, but to make things a little bit more interesting, what we can actually do is have maybe 2 different racers, right? So we could say racer 01 await, and then racer 02 dot await as well. And then we'll go ahead and say print best lap time for racer number 1. And then we'll say best lap time equals racer 02 dot await, and we'll make that a mutable variable so that we can overwrite its value. And then we'll copy that line down here. And so now we're awaiting racer 01. We're assigning the best lap time. We're awaiting racer 02, and then we're printing the best lap time again. Now, the only thing that I'm going to do differently here is to customize the lap times for racer 02. So we'll go into racer 02 and we'll go into laps right here. And we'll go ahead and let's say do lap times actually. So that's the vec that contains our different lap times. And then I'm going to pop a value off the end of that. And we want to make that mutable as well since we are customizing the vec values. And then I'm going to do racer02.laptimes.push, and I'm going to push a lower value, like maybe 57. So 57 should be less than all of the other default lap times. So previously 64 was the default, but we're going to override that with a lower lap time of 57. So racer number 2 should have a best lap time of 57 this time. So now we've got 2 different racers, and we are executing all of those right here. Now, for some reason, we are getting the same thread ID for all of these, even though we are multi-threaded. We do have 10 worker threads here. Let's go ahead and just eliminate the worker thread specification. I don't think that's going to change anything, but let me see what's going on here really quick. All right, I see what's happening here. I totally forgot that I need to actually spawn these on separate threads. So let me show you that API really quick in the Tokio documentation. So let's do a quick search for spawn right here. And so inside of the Tokio runtime, so inside of that async main function, we can actually call this spawn function right here, and we can pass in a future, and then this will give us a handle. So we can actually spawn multiple futures at the same time, and then Tokio will basically take those and it will delegate them out to different threads. So we need to just change this code a little bit here because basically we're just awaiting inside of the main thread. We're not having that delegation happening. So instead, what we want to do is call the Tokio, and then we're going to drill into the task module here, and we're going to call this spawn function, and we're going to pass in racer 01. And we're going to pass in racer 02. Now, each of these are going to return. So let's remove await here really quickly. Each of these are going to return a handle. So let's just maybe hold on to those for a second. We'll leave those errors there and we'll fix those in just a sec. But these are going to return a handle. So let's do let handle 01 equal the result of that. And then we'll say let handle 02 equal the result of that. So we've got these join handles that are basically going to allow us to monitor the completion of these 2 different futures. And you could spawn 100 futures or 1,000 futures. It's really up to you. But this spawn function here is really what's going to do that delegation to multiple threads on the Tokio runtime here. So now what we want to do is take a look at handle 01 and 02. And what we've got are these isFinished functions that we can use to check the status of the future. Is the future pending? Is it finished? And if it is finished, then we can go ahead and resolve the final value and use that data inside of our printline functions here. So what we're going to do is basically just create an infinite loop right here. And we're going to be polite by just sleeping on the main thread here. So we'll do a standard thread sleep and then standard time duration from milliseconds. And we'll just go ahead and check every, let's say 300 milliseconds to see if they're finished. Now inside of this loop right here, what we want to do is say if handle 01 dot is finished and handle 02 dot is finished, then at this point, we know that both of those racers are finished, and we can go ahead and use those values from those join handles, right? So the join handle is wrapping the final value that we want to get access to. And so inside of here, we'll just say all racers have finished. And then we can go ahead and break out of the loop because all of our racers are complete. So now what we want to do is to go ahead and get the actual values. So what we'll do is go into the handles right here, and we'll retrieve the value from those handles. So we want to get access to the final race value. So what we want to do is say handle 01. So down in these print line statements, we're just going to have a result for racer 1 and for racer number 2. So we'll plug in two different variables here and say best as a prefix here, just so we can have a different variable name to hold those. And we'll say best lap time for racer 01 and best lap time for racer 02. And then we should be able to go ahead and populate those variables from the handles. Now, I thought the join handle actually had a way to get the underlying value from it, but I can't seem to find one there. But because we have access to racer01 and racer02 here in the main function scope, we can just come down here and say racer01 dot best lap time. And then we can also grab racer02 and specify best lap time. And I think what we probably want to do is to move these statements into the poll function here. So what I'm going to do is just say, let's just do this in the poll function. So after we've completed all laps, we'll just say best lap time for person name was X, and then we'll do references to self.name and self.bestlaptime. So the reason we couldn't do that right up here is because the racer01 and racer02 are actually getting moved into the spawn calls right here. And so we don't have access to those later on, but we can go ahead and just print those details right before the poll function finishes for the last iteration. So now, if we do a cargo run here, you can see that the thread ID that's getting assigned to each of these units of work is actually different each time. And every single time that we run this, it's going to go ahead and assign to different threads. So you can see it's choosing any worker from 2, 3, or 4. And we could go back and add in the number of worker threads and set it to something like 10 here. And so now when we run, you can see it's any random thread from, I guess, number 1 through, or maybe number 2, all the way through 12, I guess, potentially. I'm not exactly sure where those thread numbers start and end at, but as you can see, we are getting scheduled on different threads right here. So if I change the racer name as well, that'll give us a little bit more clear output here. So we'll do racer number 2 dot name, and we'll set them to Sergio Perez dot toString. And so now when we run, now you can see Sergio Perez is running laps and Max Verstappen is running laps, and each of those laps can get assigned to different threads. So we've got thread number 9 doing some work, thread number 2 doing some work, and so it's just kind of dispersing these tasks all across different threads in our Tokio runtime here. So anyway, I just wanted to kind of show you Tokio as well as how to implement the future trait. It does take a little time and just practice in order to understand how this future trait works, but really the bulk of the work is being done inside of this pull function here as far as making a little bit of progress on whatever kind of data structure it is that you're working with. In this case, we have racers and individual laps. Those are the individual units of work that we're scheduling, but it kind of just depends on the structure of the application that you are building. And then once you give control back to the executor, then the executor can use that processing capacity for some other feature that may be scheduled on the same thread. So anyway, I hope this gave you some insight into Tokio as well as the future implementation here of the future trait that's in the standard library. And I guess we didn't have time to get to the other syntax of Tokio where you can actually use the builder pattern, but I'll save that for another video. In any case, again, please provide your support to this channel since I'm an independent creator. Leave a like on the video, leave a comment, check out the affiliate links in the pinned comment down below, and make sure that you share a link to this playlist and this video with your friends, family, and anybody else who you think is interested in Rust programming. Thanks again for watching, and we'll see you in the next video. Take care.